Alright, everybody. A couple things before we get started on Lab 2. I'm sorry, Lab 3. Lab 2 is due for y'all today, so I'll need to see your boards running the 4-bit fast adder before the end of the day. If you can't get it to me before the end of class, just send me a video. And then your report also is due tonight by midnight. If you tried to submit it earlier and it didn't let you, I've opened it up again so you can submit it. Couple other things. I've been getting a lot of questions about how to do the timing analysis that's required of every lab. You can actually find the walkthrough on how to do that under the Files tab right here, Quartus Timing Analyzer, and that'll guide you through getting exactly what they want. So that's pretty straightforward, not too difficult. Not loading on mine because I have to download it, but it's right there. You can download it or open it up, and that'll guide you through how to get all the timing analysis information. And then right here is how you get the total area that's required. They always ask for. This is after you compile, you get this table of contents here on the right, and if you expand where it says fitter and go down to resource section and then go down to partition statistics, this will tell you total logic elements right here is what you're looking for. Can I close this? Here we go. So that's right there is what you're looking for. Cool. And that's the number of total logic elements, so that's what they mean by the total area. So, yeah, you can just give me basically this number here, or like all of this stuff, that table there in your report. Pretty straightforward, but I wanted to cover that because there's been a lot of questions about it. All right. If you're having problems with Lab 2, after the demonstration I can go over anything that you're still struggling with, or if you need to check anything off, we can do that too. So I'm going to open up a project. Under Recent Projects, I'm going to go to my Lab 3 project here. All right. And today's lab is all about learning how to use behavioral logic, or behavioral syntax, to synthesize logic in Verilog. So far we've done assign statements, we've done gate level statements. So now we're going to learn how to model combinational circuits using basically by modeling behavior instead of modeling explicit connections. We just say this is how we want our circuit to behave. So the lab handout, if you open that up, it gives you the design specifications, and they're pretty straightforward. We have a 4-bit vector A and a 4-bit vector B as inputs. We have a binary input C. When C is 0, we treat A and B as unsigned. When C is 1, we treat A and B as 2's complement signed numbers. And then our outputs are thus. When A is greater than B, we get 1, 0, 0. When A is equal to B, we get 1. We get F2 is 1, F1. How's that? When A is greater than B, F1 is equal to 1, F2 is equal to F3 is equal to 0. When A is equal to B, F2 is equal to 1. That's how it is. Okay. Yeah, so pay attention to that because they're not all in the same order. F2 is equal to 1, F1 is equal to, F3 is equal to 0. And when A is less than B, F3 is equal to 1, and F2 and F1 are equal to 0. So basically, it's just 0, 0, 1, 0, 1, 0, and 0, 0, oh, and 1, 0, 0. All right. So we can go through that, and you can look through that on your own. And we're going to go talk about how we're going to model this using behavioral logic. So we'll create a new Verilog file. And I will call this module lab 3. All right. 4-bit vectors. We know how to declare those at this point, right? That's not anything new or exciting. So what should go here if it's a 4-bit vector? Right there where my cursor's at.
Wire, whatever name we're going to call it in square brackets.
Yeah, close, except for that the 3, 0 comes after wire. If you do it the other way around, you'll get an error. But yeah, same idea. So input wire 3, 0, A, B. We have an input wire C. We have our output wire, and in this case it's actually going to be an output reg. I'll explain why in a minute. But our reg is going to be a 3-bit vector F. Cool. All right. So the first thing to note here is that the greater than, less than, equals to operators are unsigned in Verilog. So it treats A and B or C or whatever as unsigned when it does those comparisons. There is a way to cast it to a signed value, but there's a whole bunch of gotchas about that. So for the most part, try to avoid it if you can. It will come up in 3710, and you'll learn more about it then. But for now, we're going to assume that we can't tell Verilog to treat these numbers as signed, and instead we're going to have to come up with an algorithmic way when dealing with these numbers of determining which is greater than which. So, you know, is A greater than B, is A less than B, that kind of stuff. So, what can anyone think of an algorithm that might help me, or at least the start of an algorithm that might help me to start figuring this out? Like, what operation can we perform that might at least give me the information I need? Any thoughts? If I was going to say, for example, this number is less than that number, A is less than B, and I wanted you to prove that that was the case, one way you could go about doing that would be to do A minus B and determine whether or not you have a negative number, a positive number, etc., right? That's what we're going to be doing for the algorithm. We're going to be subtracting A minus B and looking at the sign bits. So let's do this. Let's map out all of our cases that we have. Making truth tables is not super easy to do in ASCII, so I'm just going to write it like this instead. I say, first of all, let's look at the case of the different signs that we might have for A and B. So we say, if A, so case negative A, negative B. And then we also have the case negative A, positive B. We have the case positive A, negative b, and we have the case negative or positive a, positive b. So those are our different combinations of signs that we can have. And then so for each one of these, we need to figure out, assuming that we have some value, we'll make it in a minute. Let's say we have some a, or a min b equals to a minus b, like that. So whenever I reference a min b, that's what I'm referring to. Alright, so in the case of negative negative, we have the case that a is less than b. We have the case that a is greater than b. We have the case that a is equal to b. And we'll do that for all of our different cases. So paste that in there. Paste that in there. And in there. Alright. So if a is less than b, and a is negative and b is negative, then what is the sign bit of a minus b? If a is less than b and we subtract a greater than negative number, then we end up with a more, we end up with a is less than b, so we subtract a greater negative number, which means we add that number. So let's think about that. I'm just a little bit, it always trips me up. So let's say, just as an example, negative 1 minus, or it would be easier to do negative 2 minus negative 1. They're both negative, b is greater, then I end up with a negative number, because when this becomes addition, it isn't enough to overcome the negative a. So yes, negative. Cool. Which means on the other side then, if a is greater than b, then we must have a positive number. And of course, when a is equal to b, then a minus b is just, so a min b is equal to 0. And I'll actually be a little more explicit about these two. A min b is negative. A min b is positive. Alright. Now in the case that a is negative and b is positive, this is always true, right? A being less than b. A being greater than b. Well, that's not possible. And a being equal to b is also not possible. So these essentially become don't care conditions, each one of them for, or at least those two become don't care conditions for a minus b. Let's look at what happens though, even though this is always true, what happens when we subtract negative a and positive b. A is less than b, we get a more negative number, right? So just to have it here, we will say a min b is negative, always true. Alright, then positive a and negative b is the same kind of situation. This is never true, not possible, so this becomes a don't care condition. A being greater than b is always the case. What happens when we subtract them? We end up with a positive number, right? So So A min B is positive, is always true. And this is another not possible, don't care condition. Cool. All right, and then positive, positive. If A is less than B, we end up with a negative. If A is greater than B, we end up with a positive. And of course, if A is equal to B, then A min B is equal to 0. All right, so these are all our cases for the signed condition. Now there's a pattern here that will allow us to greatly simplify this logic. If you guys look at this, can you see what the pattern is? There really is only one case. Right now we have all the cases written out, but the truth is there's really only one case. Or only one... There's one set of logic that defines every case, is what I mean to say. If you look at this logic, A less than B, then A minus B is negative, right? A is greater than B, then A minus B is positive. And if A is equal to B, then A minus B is 0. Let's look at this case. If A is less than B, then A minus B is negative. Same as this case. Right? These two aren't possible, so we can ignore them. In this case, if A is less than B, that's not possible, so we can ignore it. But if A is greater than B, that's positive, which is the same as this case. And in this case, A being less than B is negative, A being greater than B is positive, and A being equal to B is 0. So in a signed situation, we always know which one's greater just by performing subtraction. Does that make sense? So our logic really just boils down to these three cases, regardless of the signs of each. Cool. All right. Unsigned is easy because we can just use the comparison operators. Greater than, less than, equals to. We don't have to do any sort of algorithmic work. So now the fun part, we get to create this logic. So we've come up with the three cases, and now we need to implement the logic in a way that we can check these cases. So the first thing we need to do is what? According to what we've written out here, what do we need first? In order to perform any of this logic, we need a value. And what value is it that we need? They all depend on a variable that we say exists. We need A minus B, right? If we don't have A minus B, we can't do any of this work. But A minus B is easy to get because we can just use the assign statement that we are comfortable with. First, I'll make a wire for A min B. So I'll say wire. It's going to be a 4-bit vector. I'll call it A min B. And I'll assign A min B equals A minus B. Like that. So that's easy. That's all syntax that is not new. It's very familiar to you all. So the new stuff comes when we want to make these various comparisons, these three down here. So to do that, we're going to use what's called an always block. And the syntax for an always block is always, and then an @ sign, and then the sensitivity list that we want to watch. So what we're saying when we put A, B, and C into this always block is that anytime A, B, or C change, we want to execute what's inside this always block. There's another way to do it. You always need to begin and end on your blocks. The other way to do it that you'll see often if you're looking at examples on the web or other places is something like that. And what that asterisk means is that we're going to let the compiler decide what the sensitivity list should be, just based on what's inside the block. It's very common. You'll see it a lot. Dr. Kalla, I talked to him about this and told me not to use it because you cannot depend on every compiler behaving the same way. Quartus compiler behaves one way. Xilinx compiler maybe behaves a little bit differently in different senses. So it's best to be explicit so that if there are bugs, you know where they're at. Different people have different opinions about that. It's one of those things, you're going to find people who insist on using the asterisk all the time. Other people who say, no, you should use the sensitivity list. I don't know. I guess it's up to you, but this is the way Dr. Kalla wants me to teach it, so this is the way I'm going to teach it. All right. So the nice thing about an always block is that we can define behavioral logic sort of like we would in C code or other places. So we can use if-then statements and other types of things that we're familiar with inside an always block. And that's actually what we're going to do in this case, is we are going to say if, first of all, we want to check our C value, right? Because if C is equal to 1, then we want to use this A minus B logic. So begin and end. And then else, begin and end. So C is equal to 1, we'll use, this is signed. So we'll use the A minus B logic here. So now, how do we get the sign of a number in 2's complement? Yeah, check the most significant bit, right? So we can say if A min B square bracket 3 is equal to 0. That's a positive number. Well, first thing we need to check actually is for equality, right? Because we always need to check equality as the first case. Otherwise, it's ambiguous if it's a positive number in case that it's like saying that it's greater than B, or if it's 0. Because if it's 0, the third bit's always going to be 0 as well. So let's check equality first. So we'll say if A min B is equal to 0, then this is equals, or A equals B. Else if A min B 3, right? That's the most significant bit, is equal to 0. Do some stuff. Else do some other stuff. It's pretty straightforward. I don't think there's any like surprises in this code at all. We're just checking the sign bit. And that's in the case of signed behavior. And then in unsigned behavior, it's really simple because we can just use this kind of syntax. If A is greater than B, begin, and etc. Okay. And then I will leave you with just this little bit of advice for your F, rather than this. So don't do this. F square bracket 3 equals F square bracket 2 equals, etc. So don't do that. Instead, do this. F equals 3 tick B, whatever you want. That's a lot faster and cleaner and nicer. And it means the same thing. Okay. Oh, and I said I was going to explain why F needed to be a reg out here. That's because in order to do this kind of assignment, like F equals this, then F needs to be of a variable data type, and a reg is a variable data type. It can change its value from one state to the next. Whereas assign, you can think of like a constant. Once it's assigned, it cannot be changed. All right. Are there any questions about this? Does all make pretty good sense? Yeah. You have a question? Oh, okay. Cool. In that case, I will go ahead and stop the recording and answer any questions you might have about Lab 2. So let's go ahead and stop this recording.